I think all of you have an idea of what negative feedback amplifiers are all about. What is negative feedback? What's that? I can't hear. What is negative feedback? What do we do when we make a negative feedback system? We sense the output and see how far it is off from the desired output and somehow control the output. Okay? So you sense the difference between the desired output and the actual output. And you use the difference to control the output. Okay? That's what we do. So, and the examples are quite familiar. Let's say you're driving a vehicle, a car, then you want to have a speed of 50 kilometers an hour, and let's say it's 30. Then you press the accelerator so that the speed goes on increasing until it reaches 30, and then you stop accelerating. Similarly, if it was above 50, then you would have started braking, and the car goes on decelerating until it reaches 50. Okay. So essentially, as long as there is an error present, you keep ramping up the stimulus, whatever that is. In this case, it's acceleration. Or if you are adjusting the volume control knob of your radio, if the volume is not high enough for you, you go on increasing it. If the volume is too high for you, you go on decreasing it. And then you stop where the error goes to 0. Okay? That's what you do. So let's say in this particular case, I'm not talking about cars or radios, but an amplifier which has a gain of K. And I want to realize this using negative feedback. So what do I sense and what do I control? Of course, I control the output V0, but what is it that I sense? What should I sense and what should I compare it with? I sense V0 and compare it with KVI, but I don't have KVI yet, right? I haven't made. Yeah, so what you do is instead you attenuate the output, right? So we can't take V0 and compare it with KVI. That means that I have another amplifier which is providing me with K times VI. Okay, so this can be written as V0 by K equals VI. If I somehow force 1 over K times V0 to be equal to VI, I have my amplifier. Okay, so K is more than 1, it's an amplifier. So V0 by K is an attenuated version of V0. I compare that to VI, and what do? I ramp up V0 if this error is positive, and if I ramp down V0 if this error is negative. Okay. So the first thing for me to do is, if I have a certain V0, I have to attenuate it by a factor of K. I'll show it as a block of 1 by K. So here I get V0 by K. Okay. And I have the input VI. So I sense the difference between these two. And what should I put here? Huh? Amplifier with why? Why? We want? Infinite gain amplifier. So what I just described was that if VI is more than V0 by K, I should go on increasing the output. Okay, that is, this is the action I want. let's say if Vi is greater than V0 by K, then what should I do? Then V0 versus T versus time should look something like this. It should keep on ramping up, right? And if Vi is less than V0 by K, it should keep on ramping down. This is the action I want, right? I mean, think of what you would do in a vehicle to get it to the right speed. This is what you do. You keep on increasing its speed until it reaches the right value. And also there is a certain sense of proportion. Let's say the difference between Vi and V0 by K is very large. Then you should ramp up quickly. That's what you do, right? If your speed is 10 kilometers an hour and the desired speed is 50, then you ramp down and then you press down on the accelerator pretty hard. But if your desired speed is 50 and your actual speed is 45, then you do it a little more softly. Okay? So there is a sense of proportion also. Right? So this is what I want. I want the output to ramp up if the error is positive, and also I want it to be proportional to the difference, or at least some way be dependent on the difference. So what is the block that will give me this type of behavior? Integrator. Is that convincing to everyone that this is an integrator? Is that okay or no? So if Vi is more than V0 by K, I do this. Okay. So if I have a given value of Vi minus V0 by K, which is the error, then I ramp up the output. Okay. If the error is negative, I ramp down the output. So what I need here is really an integrator. And I also want the rate of the ramp to be proportional to the difference. Okay. So that seems like a sensible thing to do. If the difference is very small, I don't want to ramp at a very high rate. I want to ramp at a relatively slow rate. The difference is very large, I want to ramp at a high rate. Okay. That seems like what you would do in real life also. So I'll make it, instead of just dependent on the input difference, exactly proportional to the input difference. So I'll say that the slope is some constant. I'll come to the meaning of this constant later. Okay. So if Vi minus V0 by K, here for these curves I obviously assume that Vi minus V0 by K is a fixed quantity, right? Or the input to the input is a fixed quantity. So if that's the case, then the output will ramp like this. Okay. If it's not clear, let me know. I will explain it again. So what the function I need is that this is some constant times the integral of the difference. So when does this system reach steady state? When will the output stop changing? When will the output stop changing? When the integrator input is 0, right? That's the only way the integrator output is going to be a constant. So it reaches steady state when this is 0, which means that Vi equals V0 by K, or V0 equals K times Vi. For illustration, let's assume that Vi is constant with time, that is, Vi is not time varying. So if Vi is a constant, let's say V0 is less than the desired value, the output will keep ramping up until it reaches the desired value, and then the error here will become 0. Okay. then the integrator will stop ramping or stop changing its output. So the output will be K times the input voltage. Okay. Is this clear? So in steady state, it's an amplifier of gain K. So this is how you would make a negative feedback system. So to make a negative feedback system, you need an integrator in the forward path, right? So you integrate the difference between the input and or maybe some fraction of the output and the input, and drive an integrator using it. So the integrator reaches steady state only when the input is 0. So that means that the error that you sense, that's the negative feedback sensing error, that is 0. Okay. So the output will be a desired function of the input. And you can easily see that if the feedback path, it doesn't have to be linear. It can be some non-linearity. So let's say the feedback non-linearity is an exponential. Then the function will be that the exponential of the output equals the input, which means that the output is the logarithm of the input. So you can realize non-linear functions also using negative feedback. Okay. For our discussion will confine to linear amplifiers, but as long as you have some known non-linearity, you can generate the inverse non-linearity using negative feedback. Okay. So let's take the system and analyze some characteristics. So we already know that the forward path needs to be an integrator, and once you do this in steady state, here I am talking about a constant input. Okay. In steady state, V0 equals K times Vi. So when I say constant input, that means it's a DC input. It's the DC picture that I am talking about. Okay. If you apply a constant input, wait for a long enough time, the output will be K times the input voltage. Okay. So we have made an amplifier that gives you a gain of K for at least in the long term. Okay. So let's say, so now what will happen? Let's say to start off, Vi is a certain value. Again, Vi is constant with time, and V0 is not equal to K times Vi. Okay. So V0 at time 0 is not equal to K times Vi. What is going to happen? So what will happen to the output? So let's say, again, the x-axis is time, and this is the desired output K times Vi. Okay. But for some reason, the state of the integrator is higher than this to start off with. So this is V0 at time 0. So what's going to happen? It will reach kVA at infinity, but how does it? Does it do this? Sorry. So does it do something like this? Or what does it do? It will actually be an exponential, right? We can derive it and see. Are people familiar with this? This is a first order system, so it will behave like an exponential. So this is what it will do, the second curve. It will asymptotically reach K times Vi. Okay. So what happens is, when in this particular case we took V0 of 0 to be more than kVi. Okay. So initially the error input here is negative. So the output will decrease. That will actually further reduce the error. So the rate of the output will also decrease. Okay. So that gives you an exponential. So as the output approaches the ideal value, output approaches k times Vi, the error goes to smaller and smaller values. So the ramp rate becomes smaller and smaller. Okay. So that's what you see. That's an exponential. Okay. Now we can derive it exactly. So it's quite simple. So all we have, remember this is omega u times integral of the quantity here, the error. So this quantity can be alternatively written as 1 over omega u, the derivative of the output. Right? So this is how we set up the differential equations. So we see that this equals Vi minus V0 divided by K. What is the solution to this? We know that it asymptotically reaches kVi. We want to find out exactly how. What is the function that governs the behavior of V0? Yeah. What happens to this quantity? V0 of 0, the initial condition. I am assuming that you know how to solve equations of this type. This is a first order differential equation, and especially in this particular case when Vi is a constant, you can do dV0 divided by the right hand side and integrate that, which will give you a log and so on. So to get the solution to the first order equation. So I'll write out the solution. So what you will get will be kVi 1 minus e to the minus something times t. What is the something here? Omega u by k. It will, if you take omega u to this side, whatever is the coefficient of V0 in the first order differential equation, that's what you get here. Okay. Now this is the response to the input. Okay. This is the forced response. If you remember the solution to differential equations, there is a natural response and there is a forced response. This is the forced response. And the natural response comes because of the initial state of the system. Okay. So whatever the initial state is, that will decay to 0, and whatever the forcing function is, Vi, the output will reach the output corresponding to the forcing function, k times Vi. Is it okay? You can see that as t becomes longer and longer, the output tends to kVi, right? So this part becomes kVi and this part becomes 0. So now if I want to make the system reach steady state faster, what do I have to do? I want the same amplifier. I want a gain of 10, let's say k is 10. But I want, it takes some time to reach the output. I don't want to wait that long. Maybe for my application, I need it to go faster. What do I have to do? Increase omega u, right? So omega u is a measure of the speed of the system. Okay. So we'll see this in the frequency domain also, but in the time domain itself, we see that if omega u is larger, it will do something of this sort. Okay. And if omega u is smaller, it will go more slowly. So depending on your application, you may need higher or lower speed, and you choose your omega u appropriately. Okay. Omega u must increase if you want to increase the speed of the system. Okay. So that will come to be a challenge, as we'll see later. Okay. Now, let's say I had an amplifier of gain 10. Now you were asked to design an amplifier of gain 20. What's the obvious thing that you would do? You already have a complete design of gain 10. So are you going to start the design from scratch, or what are you going to do? I'll simply change the attenuator, right? So I already have everything designed, and I have a gain of 10 that's working properly. Now I want someone asked me to design an amplifier of gain 20. So the first thing I would do is take my old amplifier and change the attenuator from a factor of 10 to a factor of 20. Okay. So will that work? That will work, right? That will give me a DC gain of 20. What else does it do? What else does it do? Look at this equation and see. So clearly, the new value of gain has been achieved, as you can see from this equation, okay, by changing the value of k. So I look here, I get whatever k is, I get that to be the gain. But if you look at this equation, k appears in the argument of the exponential. So if I increase k, it will slow down the system. Okay. So that may or may not be okay. So that depends on the constraint that's given to you. So if you're asked to design a gain of 20 amplifier, you should also ask if it should be as fast as before. If it needs to be as fast as before, then you also have to change omega u. Okay. So the speed depends not only on omega u, but also on the closed loop gain k. So if you have to have a large closed loop gain k, you have to start with a higher value of omega u. Or if you just take a feedback amplifier that's available and increase its gain, it will slow down. Okay. And increasing k reduces the speed, obviously for a given omega u. Okay. So thus far we know this much about the negative feedback amplifier. The speed depends on this constant of the integrator omega u. Okay, we'll give a meaning to the constant soon. And also the speed depends on the closed loop gain and the constant. Okay, it depends on both of them. So this equation describes what happens when you have a constant input Vi and the output is not the desired output. Okay. Now, we are not interested only in DC inputs, okay? We are also interested in higher frequency inputs. So what happens if you go to higher frequencies? Let's say now we talk about sinusoids, right? We put in sinusoids at different frequencies. How do you analyze what happens to the output? So in case of DC, we know that the output will reach k times the input voltage, okay, if you wait long enough. And also how long you have to wait depends on this constant omega u and the gain k, okay, and that can be adjusted by maybe increasing or decreasing the constant omega u. So that is for DC inputs. Now what happens if you have the input instead of being a constant, it's a sinusoid? Will the output be k times the input sinusoid? Will the output be k times the input sinusoid, or will it be something different? What is it going to be? How would you go about calculating it? Okay. Yeah, firstly, if somehow we imagine that we don't know what the exact answer is, but the logic he described is correct, that if the input is a sinusoid, and let's say the output is k times that sinusoid, then the difference is 0. So we have a case where the difference, the input to the integrator is 0, but the output is varying, like a sinusoid. That can't be the case, right? Is this clear? We assume that the output is k times the input, that gives us a result that the input to the integrator is 0. But if the input to the integrator was 0, the output would be constant, not a sinusoid. So clearly, the output will not be equal to k times the input in case of a sinusoidal input. What is it going to be? What's that? Yeah, so the error also could be some kind of a sinusoid, so that the output is a sinusoid and the error is some sinusoid, and the whole thing should be consistent. Okay, that's what happens in steady state. Anyway, we can solve it by solving the differential equation, or we'll use the Laplace transform just for the sake of exercise. Okay. So let's say this is the input. What is if we have to do Laplace transform analysis, what do we have to do first? We have to find the transfer function of the system. Right? What is the transfer function of the system? What's the transfer function of the system? How do I change this to the Laplace domain? The difference is a difference, and the attenuator is still an attenuator. What is the integrator? Omega u by s. Okay. So what is the transfer function V naught by Vi? What's the transfer function? Omega u by s. Yeah. So that's correct. So what I would prefer to write it as so that the DC gain is factored out. Okay. And it has one pole, right? Where is the pole? The pole is at minus omega u by k, and that's the argument you see in the exponential also, multiplying p. Okay. So there is a single pole at minus omega u by k. So we have the transfer function, and what is the Laplace transform of the input? If this is the input, what is the Laplace transform? Yeah. So the Laplace transform of this is s times Vp by s square plus omega square. So the output will be Now you can evaluate this. The way to do that is to separate it as two terms which have denominators like this. Okay. So something, there will be something here, and this will be some constant, and this will be of the form as plus b, right? So in general that will be the case, and so that will be the output. So I'll leave it to you to do it. Maybe after the class you can do that. So what is this? If you look in the time domain, what does this give you? Exponential. It gives you a decaying exponential. What does this give you? Sinusoid. It gives you a sinusoid, right? It gives you some sinusoid. So this exponential is a result of the pole of the system, or it's a natural response of the system. So you have some transient. Okay. Eventually this part will die down to 0, and you will get the steady state sinusoid. Okay. How can we get the steady state magnitude and phase directly? So you can evaluate it. You will get it as the sum of two terms, one of which is a decaying exponential, the other one which is a sinusoid with some phase, because I have as plus b, so that it contains a cosine and a sine, right? So it has both, and you can pretty easily work it out. So now let's say I am not concerned with the transient part, I want to just calculate the steady state part. How do I do that? Yeah, I substitute s equal to j omega and find the magnitude and phase. That's all, right? So once I substitute s equal to j omega, I get only the steady state solution to a sinusoid of frequency omega. Is this clear or no? So that's what I described yesterday. You have a h of s, and you take h of j omega multiplied by, h of j omega, it has certain magnitude and phase. That tells you how much the magnitude of the input sinusoid is modified and how much the phase of the input sinusoid is modified. Okay. So this is what I have, and at j omega I get everywhere I flip the terms, it's k by omega u. Okay. So the magnitude is and the angle is what? What is the angle of the transfer function? Minus tan inverse k omega by omega u. Okay. So omega u by k is the pole of the system. So you get the input frequency divided by the pole in all these expressions. Okay. So what can you say from this? If the input frequency is very small, then the phase difference also is going to be small, right? And the gain is going to be close to k. Okay. If omega is very small, the second term here is negligible. So the gain is going to be close to k, and the phase difference is rather small. Okay. So it will behave approximately like an amplifier of gain k, but not exactly so. Okay. Now, if as the frequencies increase, as the frequency omega increases, it could be that this omega by omega u times k becomes much more than 1. In which case the gain is much smaller than k. Okay. So the gain of we wanted to make an amplifier of gain k. And from frequency domain analysis, we see that for low frequencies, the amplifier's gain is indeed K or very close to it. But as the frequency increases, the gain drops off from K. Okay. And also, if you look at the phase shift, for very low frequencies, the output is approximately phase aligned with the input. And as the frequency increases, the phase alignment goes away. Okay. And we can see these things. These things are plotted on a Bode plot. What's the Bode plot corresponding to this? I want to plot the magnitude versus frequency. What do I get? So, for low frequencies, it will be a constant. And if I am plotting it on a dB scale, it will be 20 log K. And where does it change its slope? Omega u by K. Okay, and what's the slope going to be after this? So, minus 20 dB per decade. Okay. So, omega u by K, we saw that it appears in the time domain expression as the argument to the exponential, and here it appears as the breakpoint in the magnitude plot. Okay. So, very roughly speaking, we can say that below omega u by K, it behaves like an amplifier of gain K, and above omega u by K, it doesn't behave like that. Okay. It doesn't behave like an amplifier of gain K. So, this is the bandwidth of the system. Okay. So, the time constant in the time domain corresponds to bandwidth in the frequency domain. Now, if you want it to be faster, I said faster in the time domain. Here I would mean that it has to be an amplifier for higher frequencies. It has to behave like an amplifier of gain K for higher frequencies. That means that I will have to move this frequency to higher frequencies. So that means I have to increase omega u. Okay, it's the same conclusion that we reach using frequency domain reasoning. Okay, and what's the angle? Yeah, so it does something like this, and it asymptotically reaches 90 degrees. Okay. So this is if we analyze in the frequency domain, this is what we get, that it has a low pass transfer function of bandwidth omega u by K, and below omega u by K, it behaves more or less ideally, and above omega u by K, it definitely doesn't behave like an amplifier of gain K. So if you want an amplifier for a broader range of frequencies, you have to start off with a higher omega u. Okay. And similarly, we see that, so what happens if I change the value of K in this? So let's say I had K of 10 initially and I make it 20. What will happen to this? So what will the Bode plot look like? It moves up. So there are two segments in the Bode plot. What happens to each of those? Both of them will move up. Huh? So what happens is the DC gain increases and the pole reduces to half the value, right? So, and the slope of this is 20 dB per decade. So this line is the same. Okay. So this is K prime. It's implicit that it's in the log units, and this is omega u by K prime. So whatever value of K you take, the latter part of the curve will be the same. Okay. This is okay or no? So because the gain is K and the pole is at omega u by K, the product of these two will be omega u. Okay. So for a first order system, that is if you have a single integrator in a feedback loop, then the product of the gain and the pole will be constant, and that constant will be this omega u of the integrator. Okay. Is this okay? So this is usually called the gain bandwidth product, and gain bandwidth product is constant, but for a first order system, that's most important to remember. Okay. Now also we did this from the Bode plot, so this is only approximately true, but for large values of k, it is quite alright. Okay. So I'm not sure if I see it here. So what we saw was gain of k and a bandwidth of omega u by k, and gain times bandwidth equals omega u, and this is generally true for a first order system. Okay, that if you have a feedback system and you change the feedback factor, and if the feedback system is of first order, then as you change the gain, the bandwidth will change in some way, and the product of the two will be constant. Okay. This behaves as an amplifier of gain k if omega is less than omega u by k. Okay, approximately. Now, what is omega u? Omega u was the constant that we took for the integrator. What is the significance? Now, by analyzing the feedback system, we see that it is the gain times bandwidth of the feedback system. Okay, but for the integrator itself, what is the significance of omega u? Not sure if the question was clear. So I have this integrator. Okay, or in the frequency domain, I have omega u by s. Okay. If I apply a constant input, okay, that's a Vp. What is the output going to be? Ramp. And what's the slope of the ramp? Vp times omega u, right? So omega u is the constant that appears in the slope. Now I analyze the same thing in the frequency domain. That is, I analyze the steady state frequency response of this. So this is T V out, and the input here is Vp. Now let's say we plot the magnitude and phase response of this. What's the magnitude response? Straight line at minus 20 dB per decade, right? So h of j omega is omega u divided by j omega. And when does the magnitude reach unity? Omega u. Okay, when omega becomes equal to omega u, the magnitude of this transfer function is unity. So that's why it is denoted omega u. It's the unity gain frequency of the integrator. Okay. And what is the phase of this? It's minus 90 throughout. Okay. This is the magnitude and this is the phase. Okay. So omega u is the unity gain frequency of the integrator that we use in the feedback loop, and it also turns out to be the gain times bandwidth of the feedback system that we make. Okay. So if we take an integrator of unity gain frequency omega u, enclose it in a feedback loop of feedback fraction k, then the gain times bandwidth will be omega u. Okay. So this is again a result that you should be familiar with. You know that op amp has a certain gain times bandwidth product, and if you change the feedback fraction, the bandwidth will change also and the gain will change, so that you get gain times bandwidth to be a constant. And this is how it happens. Okay. So let me do one thing now. Here I will plot first the magnitude response of the integrator. Okay. Now on the same plot, I want to plot the magnitude response of the closed loop amplifier. Okay. What does it look like? So I have a gain of k. Right. So the transfer function is k by 1 plus s times k by omega u. If I plot it on the same curve, what does it look like? So this, of course, we know that it is 20 log k, and then it follows a 20 dB per decade slope. But what does it look like? Does it look like this or this? Or it follows the same curve. Okay. In fact, it doesn't look like either of these. If the gain is k, it does this and then follows the same curve. Okay. So this is k, and if I change it to a different gain, maybe a higher gain, it starts from here, the bandwidth will be lower, and that also follows the same curve. Why does this happen? Is this some coincidence? Some mathematical thing that comes out? Yeah. What's that? Yeah. So actually, the gain bandwidth product is the same. That's what we calculated. I'm asking if there is a greater significance to this. So we'll see what that is. Okay. So it will in fact follow the same, and if you see the unity gain crossing of all of them is the same. It is omega u. Okay. So this is the 0 dB line, right, of the unity gain line. So the integrator gain starts off from infinity at DC. The gain of an integrator is infinite at DC, right? If you apply a DC input, the output will keep on ramping up to infinity. Now it starts from infinity, but it keeps falling down and it crosses unity at omega u. Now if you have a feedback factor of k, the DC gain is k up to a frequency of omega u by k. And after that it keeps falling and it crosses unity also at omega u. Okay. So let's see why it does this, or let's see this a little bit more. Okay. I assume that you are familiar with basics of feedback systems. Okay. And this is the classic picture that you see, right? With the letters G and H. What is y by u? G by 1 plus Gh. And what is this quantity Gh? Loop gain. What is the significance of loop gain? Right, first of all, would you want the loop gain to be large or small? Why? So the loop gain should be large so that the output, the transfer function is a function only of edge, right? Normally, the motivation for starting using these feedback amplifiers was that you couldn't make amplifiers with a precise gain, but you can make attenuators very precisely. If you make a resistive divider, that is precise. So instead of using an amplifier and trying to make its gain precise, you make some amplifier, okay, but you make a precise attenuator and put it in the feedback path. So now, under certain circumstances, the gain will be a function only of the feedback fraction. Okay, just like we saw before. So in our feedback system also, the steady state gain is dependent only on K. Okay, it's not really dependent on omega u. So maybe you make two different amplifiers and they have different omega u's. You can't control it very well, but you can control the attenuator very well. So the gain will still be K. Okay. So the gain will not be primarily affected by omega u at all. So that's the motivation for making feedback systems. Okay. So GH should be large. I'll rewrite this. This can be written as okay, or 1 over h. So if GH or the loop gain is very large, this term will be negligible and you will get approximately 1 over h. Now in general, you can't always reduce feedback systems to this block diagram very easily when you have circuits. Okay. And also the input can be at different places. But what you will see is that the gain of a feedback system is always some ideal value of gain, which is what you want to achieve, times one by 1 plus 1 over GH, or 1 by 1 plus 1 over the loop gain. Okay. So if the loop gain is very large, you will get the ideal gain. The ideal gain can be anything. That is something that you define by injecting the input to appropriate places and so on. But there will always be this multiplying factor. Okay. So if the loop gain is very large, you will get the ideal gain that you want. Okay. So what I'd like you to do is, before next week's class, find out the loop gain for our feedback system and try to figure out why the bandwidth comes out to be what it is. Okay. Loop gain calculation, and we get the bandwidth to be omega u by k. Okay. So just figure out if this is some coincidental thing or what's the meaning of this. There's no class on Friday. I'm not going to be in town. Okay. Any questions on anything that we discussed so far? So what we did was to try and make an amplifier of gain k. We realized that we can make it by sensing the difference between V0 by k and the input and driving an integrator using it. And we also analyzed it in time and frequency domains. In the time domain, we see that asymptotically the output reaches the input if the input is DC. Or in the frequency domain, we see that for low frequencies, the output will be k times the input, and as the frequencies increase, it will start deviating from that. Okay. And we also calculated some things like gain and the product of gain and bandwidth being constant and so on. So the next thing we'll do is to see the loop gain. Okay. What we'll do is to expand from here, see what for this, for our amplifier to work, we need to be able to make an integrator. It will turn out that we won't be able to make it exactly. We'll see what the effects of that is. Okay, that are. Okay.